Hello, everybody. My name is Brandon Botzer. If you're watching this, you are in the spring 2023 DAAN 572 reinforcement learning class. I'm going to be walking through you here what I did for my final project and kind of show you, what I learned within this reinforcement learning class. And, if you're watching this, sit back, relax, and let's enjoy the ride. So what I looked at here for my reinforcement learning problem, my environment, was a Gymnasium environment here. If you're not familiar, Gymnasium is kind of a standard open source API for reinforcement learning by the Farmer Foundation. They have a bunch of different environments or whatnot. You should definitely check them out. But what I focused on was a classic control task known as Acrobot. And this is our little friend, the Acrobot here. It's a double physical pendulum. So these rods here are mast rods with a pivot point at the top, binding this one, and then a pivot point connecting each of them in between. It's a discrete space. So in each space here, it exists at some nodal point in time. And effectively, the only thing the agent can do here for actions is applying a torque onto this center pivot here. We can either apply a torque on that actuated joint in the negative direction or the positive direction, or we could just not apply a torque. The action itself it's very discrete, it's very deterministic, and it's just acting on that little point, which makes this a little awkward. What the Acrobot is trying to do, and we'll look at a slightly larger picture here, what this little guy's trying to do here is he's trying to get some part of this this end piece here to go above this goal line. So we're trying to get this thing to kind of go back and forth and spin around and whip itself up so that it reaches the end height. And you can imagine this is difficult to do. That's why we use reinforcement learning for this. And it's even more difficult because within the realm of physics, this is what's known as a chaos pendulum. Small perturbations not only in the initial conditions of this pendulum, but throughout its motion can drastically change the motion of the pendulum itself. If something's just a little bit askew, half a degree off, and then you put in this exact same inputs, you can get drastically different results. So trying to solve something like this, to get it to do what you want to do is a very difficult thing to do, but it's a perfect fit for the world of reinforcement learning. So how did I go about solving this problem? Well, there are three algorithms that I actually looked at for this, and they are the A2C method, actor critic methods, deep Q networks, and the proximal policy optimization, or PPOs. In actually implementing them, I use Stable-Baselines3. If you're not familiar with this is a great resource, Stable-Baselines3. It's an open source kind of baseline. I mean, it's in the name. Reinforcement learning implementations that you can use as a framework to base your results off of, and to kind of check whether or not you're doing better than the standard methods that exist. This is a updated version from Stable-Baselines 2. Stable-Baselines 2 had a little bit more implementation in terms of the algorithms, but they've updated in order to match some TensorFlow things. And they're still building on this, and it's a very active community. But it's got all your standard base algorithms that you could use here. And the really great part about this is that all of these Stable-Baseline 3 algorithms, they'll interface with any environment set up in a Gymnasium way. So, while we see the classic Gymnasium environments here, there are many more Gymnasium environments out there as long as they're built in that same space and kind of a wrapper encapsulating them. Stable-Baselines will work with any of them. So it's a great tool to dive into this and test a lot of different algorithms and really see what is the difference between them. How are they acting? What are they doing? And what is the best way to solve out our problem of the Acrobot? A little pendulum warming around there. So one of the first methods I used was the A2C actor critic method. In short, or the advantage actor critic here is a policy gradient method with a twist. We follow kind of a standard vanilla policy gradient down, but the twist of that is we take a look at this advantage function here, where we take a look at a Q function and a state values, so Q values and state values, and we subtract them to get some advantage of what would taking these sets of decisions as opposed to just existing in these states pose here. And by kind of weighting the gradient descent in that way, we can scale a little bit faster into our model that we want to choose. So there's a little tweak there. Just in a classic gradient descent, we help it out a little bit more. There's some bootstrapping that takes in there to just help it along, which is a really nice feature. It's a nice stable policy for the most part, and it will give you results, even if they might take shorter or longer. The second method or algorithm I used was the deep Q network. Deep Q networks are nice because you can take this large aggregate of data and use a nonlinear Q network or nonlinear neural network in order to kind of pass this information through and get something. The weird piece about the deep Q network is some of the implementation it has to do in order to function appropriately. These DQNs, they use a few different tricks here. They use a replay buffer and a target network in order to move forward. And this DQN from Stable-Baselines also makes a little bit of gradient clipping in here. But the big things for a classic DQN are the replay buffers and the target networks. What a replay buffer does is it will, as it's going through these steps, it'll take a few episodes of the environment of the actor, making decisions in there. And it'll create this replay buffer, but all of those actions are tied together. Temporally, they're very correlated, and we don't want that. In order to make proper use of the neural networks, we need uncorrelated values. And so what happens is once we have this correlated set of episodes, we'll randomly sample from the replay buffer to uncorrelate them or to pseudo-uncorrelate them to some extent, and then use those and pass those into the neural network. So it kind of gets rid of that correlation that we didn't want there. The target network is very useful because what you're doing with a DQN is you're trying to run your model and have it match that DQN, that Q network there that you set up. And what will end up happening is every time you run it, when you go to compare it and then make your update, you have a value, you run compare, and then you get it a little closer, and then you update this and it moves, and then you get a little closer and it updates and it moves, and you get a little closer and you keep walking forever. You never actually finish the problem. You're chasing your own tail. The target network, it holds into position a copy of the original neural network you had so that you can get closer and closer and closer and closer and closer, and then you can update that target network to make a better representation of what you actually have based on all of the learning that you did, and then you can approach it again, and then you can update it and approach it, and eventually as you do that, you will get closer and closer to that optimal policy, which is really nice there. Con of the DQNs are you're just running large neural networks, and that can be computationally expensive. The last algorithm that I had was the PPO, proximal policy optimization. It's a fun combination of the advanter actor critic and what's known as a trust region policy optimization, TRPO. Effectively what we're doing here at its base is we are using another policy gradient method with a slight twist here. What's actually happening is as the gradient method is going down and you're going forward, there's a clipping that takes place where if the DQN, in that gradient setup, there could be a large change that is made where you go from one position like very far over to the next within that gradient descent. What the PPO does is it looks at that gradient descent and it says, hey, we're not going to let you make too large of a jump, because if you make too large of a jump, you might jump into a bad space. You might jump somewhere you don't want to actually be, but you just think you're there because you don't know enough yet. And if you keep making these large jumps, you could eventually, find yourself in a really bad spot, and then, you won't reach that optimal policy. So it forces the algorithm to take smaller steps each time as it approaches that optimal policy, and as a result, it becomes a little bit more robust in terms of, it will get there eventually. It's a little bit smoother in its learning, which is, a nice thing depending on what kind of situation you have. But those were the three that I used. Now, in terms of how I evaluated these, because these are 3 different algorithms, A2C, DQNs, and PPOs, they're all doing things a little bit differently. How did I evaluate them? Well, I ended up evaluating these using the rewards there. It's the one thing that holds constant over across all of these. The way Acrobot here, as it's swinging around, calculates rewards is that each action it takes, each step, whether it torques left, torques right, or doesn't torque at all, gives it a reward of -1. So if this just keeps swinging down here forever and it never reaches that goal height, it'll max out at a score of -500, which is the worst it can do. If it figures it out and swings up high, then it'll hit a score of negative something, some value that's greater than -500. And no matter what you use, A2C, DQNs, or PPO, we can compare those scores and see, which of the algorithms was able to figure this out in the least amount of, pivots across or torques applied to that central pivot there. So that's how I did that. It was a great metric to look across all of these. There are a whole slew more of metrics, though, that you can measure within TensorBoard. TensorBoard is a great way to look at rollout metrics and mean metrics across the environments. I ran, as we'll see in a bit, a lot of different samples here, a lot of different trials of PPOs, DQNs, and A2Cs of different time steps. So are we just going to go for 10,000 steps, 50,000, 100,000, 1 million? And when you do this with TensorBoard, though, it will run a lot of this plotting for you. So it'll actually roll out these plots as we're going along here and show you what you have. You can take them and scroll along. You can zoom in and out. It'll do this for your training metrics as well. So you can see explained variance, clip fractions, learning rates, which we held constant for this one. But there's a whole lot of things here. And depending on what you're looking at, if this is A2C, we might not have a reported policy gradient loss. But for something like a PPO, where we'll just run this one real quick, all of a sudden we have it. And it's nice to see that for this policy gradient loss, there's actually a relationship between this distance right here, this large dip we see, and the rewards that come out of this. A lot of our episode reward means actually come from that region where we saw that curve right there in the beginning to this point. So TensorBoard does this very well. It's a really nice feature. You can kind of expand these graphs, make them larger if you want to, zoom around. If you haven't checked it out, please do so. It's a really nice thing there. There are other things just like this. Some of them you pay for, some of them you can just find online, but this is totally free. Interfaces very well, and I suggest you look into it. Now, as to the actual code itself, just for time here and brevity, a bunch of imports. We make the environment using Gymnasium. Gymnasium has a bunch of built-in functions to do this. We simply make the environment, pass it an environment name, which in this case is Acrobot v1. We render it in human mode so that we can watch the pendulum wiggle around. And then we set some log paths here that we'll use later on in order to grab some algorithms and grab some models and some training stuff. To actually train these, and this is a very similar training method that happens for the DQNs, the A2Cs, and the PPOs. We run this for steps of 10,000, 50,000, 100,000, 200,000, 500,000, and 1 million steps here. And we do this 5 times for each. So, I didn't want something to happen where, the algorithm took a weird step at some point and it led it down a really weird path and we have a bad policy now. So I ran this 5 times for each of these. So 1, 2, 3, 4, 5, 6 times 5 is 30, and we did this at least 3 times. We actually did this 6 times. So there's a lot of trials going on here. One of the other things that we were able to do with Gymnasium is not only did we run this for many time steps and many trials, but in this we were able to speed up the learning by vectorizing our environments. We were able to create 4 environments here and train on them in parallel and then bring them back together. We're really only limited there by the size of your CPU or GPU, whatever you're using. So that's kind of a neat feature here. And then we go through, we step through everything. We reset the environment. So we initialize it to some random state, noting that once again, those random states are very important for a chaotic pendulum. We set up a model. This object here is a DeepQ network. We pass it a multi-layer perceptron policy for the environment. And then we have it output everything, and we give it a TensorBoard log path here so that we can keep track of all these logs. we simply ask Gymnasium to run some learning on this, run it for all the time steps that we want, 10,000, 50,000, 100,000, all the way up to 1,000,000. We log that out into the TensorBoard area with a log name, and then we save that model so that we can grab it back later, which we'll see some models at the end of this. And then we do it again, and again. Once we're done with that, we reset the environment, we close it all out, and it runs 5 new trials for more steps. We did this, like I said, for DQNs, PPOs, and A2Cs, but we also took a look at this, and when I say we, I keep saying we, I mean I, old habits. We also did this for optimized features of this. So for the DeepQ network, the Advantage Actor Critic, and the Proximal Policy Optimization, there are actually optimized hyperparameters to each of these. So we ran exactly what we did again, but for optimized hyperparameters, we see that we set up a slightly different neural net architecture here. Instead of a 64-64, we went 256-256, fully connected, and there's a lot more hyperparameters. Luckily, I was able to pull these hyperparameters from the reinforcement learning zoo, so that they did a lot of this optimization of these previously. I was able to test that out and see what the gains were. And we did this for DQNs, PPO, and for the A2C. So as I scroll down and my screen loads, because there's just a lot, they're all here. Now to actually see what this looks like, once we created all of these things and we want to, actually pull them back up, we can test these models out by loading them and then evaluating the policy. So what I'll do real quick is I'll take the DeepQ network, only ran for 10,000 steps for this trial 1 here, and then we're going to evaluate it and see what comes up here. So I'll just create that environment. I'll do one environment, so it's just one running, and then we'll evaluate it and we'll see what solution actually pops up here, what policy. So when we run it, we get our little thing here. It moves very, very fast. But we see that we just have some wiggling back and forth, and it never actually flips up to reach the top. So in that one test, we didn't reach the top. We had a negative 500 here. To get rid of this and to unfreeze things, we'll close and reset. And we see that that 10,000 time step trial did not do very well for the DQN. So let's load up another one and see how that one did. So we'll load that and we'll evaluate it. And this one, it's still struggling here. We get a lot of this kind of just wiggling back and forth. It never actually makes it. So let's go more steps, right? If we got more steps, let's try more steps. So we run for more steps here. And in doing so, oh, that finished very quickly. So let's actually run that again. So we'll just run it more times so we can see something happen here. We'll do it live because that one was very fast. So in this one, we can see it quickly finds this solution. So at 1,000,000 time steps, we quickly find a solution here. The DQNs have some fluctuations, some hiccups that actually happen through them as they're trying to solve this out. If we actually go back and take a look at a DQN here for 1,000,000 time steps, we see that for the mean reward here, it starts doing well, and then it dips off, and then it does poorly, and then it does well again, and it kind of stabilizes up here. So it's kind of interesting how the DQNs get better, get bad, and then kind of stabilize at this good with some hiccups along the way. But it does end up solving this out. We see we have a much better policy evaluation here. It's solving it at about, on average, 100 steps or so, and that's much better than not solving it at all. Looking at the PPO, that was for 1,000,000 trials right there. For the PPO at 1,000,000 trials, if we do a very similar thing and we run this, we see that PPO is also able to solve this. PPO actually solves this starting at around 50,000 time steps. It starts to do pretty well at this, kind of around that 120, 130 range. After running this right here, we see that PPO on average is solving this in about 66 steps. And that's the unoptimized version here. So that's actually pretty interesting. If we do something very similar with the A2C, we can load this up And when running this for the time steps, we see that A2C is also able to solve this in a very similar fashion, kind of whipping back and forth and then sending that tail end into a high kick there. When looking at these, initially, it appears that PPO is just the best result here. We've got negative 83, we've got negative 66, and we've got negative 108 for the 1 million trials. But what we actually found was that when running these for the optimized hyperparameters, we actually found something very interesting. When optimizing hyperparameters, the DQN, the DeepQ network, actually did very marked performance improvements to the point where it went from like 108 on that to negative 62. It did much, much better. It actually did better than both the PPO and the A2C model. Both of these kind of pulled around just that same 60-ish value, but the DQNs were in this like negative 62 region. So just a little bit better, squeaked out a little bit better performance, which was very fascinating. The somewhat strange part about that, though, was when looking at these optimized hyperparameters, and we'll look at this for one of the PPOs. We'll look at this for one of the A2Cs, and look at this for one of the DQNs here. Let's find, we see very similar results in terms of they all quickly move up like this and really stabilize up here. We see that the blue one, though, is that DQN. It just figures it out a little bit more. And there's just a very large Q network that it's making use of. Now, the really interesting thing about this, though, is while it did, slightly marked improvement, right? You can see a small gap here between the A2C, the PPO, and the DQN, where the DQN is the most, best in rewards. If you actually take a look at how long it took the DQN to train down here, we see that the DQN for, we'll start back here where things kind of start leveling out. It took the DQN 20 minutes to train that, where the PPO, minute 19. The A2C, 49 seconds. So, is a little bit of extra improvement enough to give you much longer run times? If you want to go all the way out and get this like little extra out here, you're talking an hour of trying to optimize that policy, where even for PPO and A2C, you're talking 4 minutes and 2 minutes. So while the DQN was, in terms of pure reward, the best, at what cost? What kind of computational time and did you have there to kind of wait for that policy to find itself? If you've got that time, great, run it. If you don't, maybe the PPO, it being nice and smooth, as we see here, is good. Or maybe the A2C jumping up quickly, making that large gap, because remember the PPO won't make that large of a jump, is what you want. So it's really pros and cons of each algorithm, what you're looking for, and how you'd like to run whatever your control task is. What are you looking for? Are you looking for instant snap feedback, or do you have more time to train? Just what are you trying to do? So it's always an interesting pros, cons, and things like that. And as a result, the project itself, was able to see that, and we were able to see this just with stable baselines, which we know to be a ground zero of these are the baselines for reinforcement learning within a very commonly used and well-researched gymnasium environment. So it's very cool there. The big takeaway from this is there's a lot of ways to tackle these problems, but in terms of reinforcement learning, hyperparameter optimization is something that must be looked at, especially for chaotic problems like the physical pendulum. Like double physical pendulum is chaotic. Small changes give large differences in where that pendulum will go. And the DeepQ network, starting with that 64 by 64 fully connected neural network, that was not a large enough system to properly understand those chaotic environments and those chaotic motions. It wasn't until we put a 256 by 256 fully connected neural network in there that it was actually able to properly, tease out what it needed to do. And you can even see right here where it kind of dips like that, where it struggles. So hyperparameter optimization, nothing to sneeze about, definitely something to look at. While you could do this in an old-fashioned grid search, I recommend looking at something like Optima. That does more of a gradient policy, gradient descent to look at your policies and your hyperparameters as it adjusts them over time. But those kind of hyperparameter optimizations, they do take time to work all the way through. So I hope you liked what I was able to find here. I hope you saw something that you haven't seen before and you got something out of this. But with that, I believe our time is done. I wish you all the best and have a great one. Bye-bye.